Rudewright Academy. Learn it, teach it, remember it. Today we'll learn consistent hashing. It's the trick that lets a cluster of servers grow or shrink without reshuffling all of the data it holds. Let me show you how it works. Picture a cache made of 4 servers, holding 1,000,000 keys between them. Every request that arrives asks the same tiny question. This key, which of my servers holds it? You need a rule. It has to be fast. Everyone who asks must get the same answer, and it should spread the keys evenly so no server drowns. And here's the real puzzle. What happens to your rule on the day you add a 5th server? There's an answer so natural that almost everyone invents it on the spot. Hash the key, which turns its name into a big random-looking number. Then divide by the number of servers, 4, and keep the remainder. A remainder of 0 means server 0. 1 means server 1, and so on. Watch it root. This key hashes to 47. The remainder is 3, so server 3 takes it. This one hashes to 132, and its remainder is 0, so it lands on server 0. And the rest fan out just as evenly. One line of code. Perfectly even. Instant. And it works beautifully, right up until the day you change the number of servers. Now traffic grows, so we add a 5th server. That should be good news. But the rule says divide by 5 now, not 4. The hashes didn't change. The remainders did. Watch the damage. This key moves. So does this one. And this one. In all, 8 of our 10 keys land on a different server than before. Only 2 stay home. Adding one machine reshuffled almost everything. And in a cache, a moved key is a lost key. Its new server has never seen it, so the request misses and falls through to the database behind the cache. Move most of 1,000,000 keys at once, and that database takes a stampede of misses. Scaling up your cache just took your system down. The root cause is the divisor. The server count is baked into every key's address, so touching the count readdresses every key. So here is the whole insight. Stop dividing by the server count. Take the count out of the address entirely. Picture the full range of hash values as one long number line. Now bend that line into a circle so the end wraps around and meets the beginning. This circle is the ring. A key hashes to a fixed point on it, and that point depends only on the key itself. Nothing else. And here's the move. Hash the servers onto the very same ring. Server A's name lands it here. B and C land at their own fixed points too. The ownership rule is one sentence. A key belongs to the first server you meet walking clockwise from where the key sits. Let's walk it by hand. Our key landed here between A and B. Walk clockwise from where it sits, and the first server you bump into is B. So B owns it. Another key lands over here, past B. Walking on, the first server it meets is C. Now, a question for you. This key lands late in the circle past C, and there's no server ahead of it before the top. Who owns it? Walk it and see. We cross the top of the ring, keep going, and the first server we meet is A. The ring has no end, so the walk always finds someone. A few more quickly. This one walks to B. This one reaches C. And this last one crosses the top to A again. Now notice what each server really owns. The arc of ring between its predecessor and itself. Hold on to that picture because it is the key to everything that follows. Now replay the event that broke the remainder trick. Capacity grows and a new server joins. Call it D. Its name hashes it here, between B and C. Before anything moves, ask the question. Which keys must move? A key only ever cares about the first server clockwise from its own spot. So the only keys affected sit on this arc between D's predecessor and D itself. These two used to walk past here, all the way around to C. Now they stop at D first. Watch. This key re-walks to D. And this one. And nobody else even noticed. Every other key still walks to exactly the server it walked to before. 2 keys moved, out of 6. On average, a new server takes over one small slice of the ring and the rest of the world never feels it. The catastrophe just became a routine. Removal is the mirror image. Say B dies. Look at the keys on B's arc, the stretch between A and B. They simply keep walking clockwise past where B used to be, and the first server they meet now is D. So B's whole slice slides to its clockwise neighbor, and every other key is untouched. No global reshuffle, no emergency migration. The geometry absorbs the failure. And in replicated systems, that neighbor usually already holds copies of exactly those keys, which is why the ring pairs so naturally with replication. But that is its own lesson for another day. The pure ring has one honest flaw, and you should meet it head on. Server positions are hashes, effectively random, and 3 random darts can land clumped. Look at this ring. A, B, and C all fell in one small stretch near the top. B owns a sliver. C owns a sliver. And A owns everything else. Almost the whole circle. Now scatter a spread of 12 keys around the ring. Root them and watch where they land. Nearly every walk ends at A. 10 keys for A. Just 1 for B. And 1 for C. 1 server drowns while 2 sit idle. Uniformly random is not the same as uniformly spread when you only throw 3 darts. The fix is delightfully cheap. Let each server appear at many points on the ring, not one. Hash its name with a suffix. The name +1, the name +2. Every hash is 1 more position for the same machine. These extra positions are virtual nodes. Now root the same 12 keys again. The walks are short and the counts come out 4, 4, and 4. Real systems give each server 100 positions or more. And there's a bonus. A server that joins with 100 positions takes 100 tiny slices from all over the ring, so the load it relieves comes a little from everyone, not all from one unlucky neighbor. For all the geometry, the code is humbly small. The ring is just a sorted list of positions, 1 per virtual node, plus a map from each position to the server that placed it. To root a key, hash it. Then binary search the sorted list for the first position at or past that hash. And if the search runs off the end of the list, wrap around to the first entry. That one line is the whole circle. Watch it run. The key's hash is 150. The search cuts the table in half and half again, and lands on 190, which belongs to A. Now the wrap. This key's hash is 350, past every entry in the table, so it wraps to the top, position 10. Owned by A again, around the ring. 4 limits decide whether the ring saves you or surprises you. First, uniform keys is not uniform traffic. If one key is 1,000 times hotter than the rest, its owner takes all of that heat and no amount of virtual nodes helps. Hot keys need their own medicine. Replicate them, cache them closer to the client, or split them. Second, a bare ring is a lumpy ring. Virtual nodes are part of the pattern, not an optimization you can skip. Third, only one slice moves. But that slice moves all at once, and it arrives cold. Real operations still add servers gradually and warm them up. The ring shrinks the blast radius. It does not remove the blast. And fourth, a cluster that never changes doesn't need any of this. The remainder trick is simpler and perfectly fine when the count is truly fixed. The ring earns its keep in clusters that churn. So what does a lookup cost? Let's count it rather than assert it. Say we run 10 servers and give each one 100 virtual positions. That's a routing table of 1,000 entries. A binary search halves the table with every look. 1,000 becomes 500, then 250. And it keeps halving all the way down to a single entry. Count the halvings. 10 looks. That is the whole routing decision. 10 comparisons in memory made once per request. That's why this scheme sits comfortably on the hot path of every cache and store that uses it. Now put the two worlds side by side. The same cluster, 10 servers, 100 keys, and both worlds add one server. On the left, the remainder trick. The keys start moving, and they keep moving. Past half of them, past 3/4. 91 of every 100 keys displaced. On the right, the ring. One slice changes hands. 9 keys move, and it is already over. The same event in two worlds. One of them is an outage. The other is a Tuesday afternoon, and you'll meet this ring everywhere that ownership has to survive churn. A distributed cache deciding which instance holds a session so that adding capacity doesn't flush everyone's data. A sharded key value store deciding which shard owns a record. The famous Dynamo-style databases are built on exactly this ring. And an edge network deciding which edge server caches which piece of content so that servers joining and leaving the pool don't flush everyone's cache. The recognition queue is always the same sentence. Given a key and a changing set of servers, who owns it? Ownership plus churn. Draw the ring. So, one more time, the whole idea in one breath. Hash your keys and your servers onto the same ring. Every key belongs to the first server you meet walking clockwise. And when a server joins or leaves, only one slice of the ring changes hands. The remainder trick bakes the server count into every address, so changing the count moves everything. The ring takes the count out of the address, so changing the count moves one slice. Keep the slices small and even with virtual nodes, root with a sorted table and a binary search, and respect the limits. That is consistent hashing. It's the reason adding a cache server is a routine Tuesday afternoon instead of an outage. Want to keep learning? Come find us at academy.rudewrite.com.